Good morning, everyone. I welcome you at the course which is named Introduction to Scientific Visualization with ParaView. This course is being delivered by our partners from NCC Netherlands and SURF. And we, as NCC, National Competence Center of the Czech Republic, are basically taking care of the organization. And the course is a basic course. It introduces participants to the fundamentals of scientific visualization using ParaView. ParaView is an accessible and powerful open source tool widely utilized in academic and professional settings. You will embark on a structured exploration. We will start with a clear distinction between scientific visualization and visualization of information, and also setting the stage for understanding the respective roles and applications. I would also like to introduce our tutors today. It's Paul Mellis and Casper van Leuven. Paul Mellis is with SURF since 2009 and works on scientific visualization and extended reality innovation. And Casper joined SURF in 2014 and focuses, amongst other things, on interactive web-based visualization. They both have an MSc master's degree in computer science. Paul from the University of Twente and Casper from the University of Delft. They have a range of visualization support and development experience regarding 3D graphics, interactive 3D visualization, and remote visualization. They work within the high-performance computing and visualization group at SURF, where they support the users of the Dutch supercomputer Snellius with visualization-related tasks. They also regularly demo XR devices and applications, develop demos, or get involved in producing visualizations for PR purposes. So today we are starting at 9. The course is planned to be just half-day course, so the planned closing is at 1 p.m. There will be one coffee break at 11:30, and you can find the agenda and all this information on the website of the course, which my colleague will put into the chat, so you can easily go there and see. And with that, I would like to thank you for coming for the course, and I would especially like to thank Paul and Casper for this great opportunity to learn from them the introduction to ParaView. And with that, I will stop my sharing, and Paul, if you could take over.
Good morning, everybody. So, of course, Introduction to Scientific Visualization with ParaView. Thank you very much for the, extensive introduction about ourselves and the course. You already mentioned this, who we are, what our background is. I just wanted to mention that we're working at SURF, and SURF in the Netherlands is it's not a traditional HPC center. It's more like an organization that does all kinds of innovation and service support and service development activities. And the main parts here that are relevant for this course are that we have a high-performance computing facility, the Snellius supercomputer, and we have a visualization team, of which me and Casper and a few other people are members. So we basically support our users that do these HPC computations with visualization. So this ParaView course is one of the activities, but we also turn people's data into animations, for example, or help them write scripts or software. So we also maintain a bit of a software stack on the system, Snellius, that you see here. This is just a part of it. It's a little bit bigger than the photo shows. So next to ParaView, we also have Visit and VTK, and Blender, for those of you that know those type of packages. So they're all visualization related packages. Some are a bit more scientific visualizations, other are a bit more into the beautiful types of visualizations. So we manage that kind of software, and we also help the users to decide on the type of visualization or the best approach for large data sets. So some of that experience from doing these things is present in this course. For example, we'll go into parallel visualization using ParaView. When you have a really large data set that doesn't fit on a single compute node, for example, how can you split that up? How can you use multiple servers and still get a nice visualization? We're also involved in different types of visualization projects and not just HPC related. Especially Casper is pretty good in building these web-based interactive front ends for doing all kinds of visualization tasks. But we also do things in 3D game engines or render nice animations in Blender, for example. All with very different types of focus. And sometimes it's really about analysis of data for a scientist. and sometimes it's very much like a PR activity for Serve itself. So the program was already shown. I tweaked it a little bit. We still have a break. It's well, slightly before 11:30, I would say. So the basic idea of the program is we start with an overview of different types of visualization, then go into more detail with ParaView, including a bit of a live demo from my side, just to give you an idea of what it can do. Then from 10 to 10:30, there's a hands-on where you can well, work on a few exercises that we provide, including some data sets. So there's different types of data, different types of visualization that you can try out really interactively. And within this time slot from 10 to 11:30, there's also the break for you to take at the moment that you'd like to do that. And then after the break, we'll dive into a few more topics, go into a little bit more detail on the data model that ParaView uses, which is important if you want to have your own data within ParaView. Also look into making things look a bit more pretty. So not just the standard rendering, but adding things like shadows or reflections. We'll look into plugins very briefly, because you can extend ParaView with small pieces of software, basically. The remote rendering for a very large data set already mentioned. We'll spend some time on that. And finally, we'll show a little bit of Python scripting. That's a very extensive topic, obviously, so we can just show basically the possibilities and give some idea of how to use Python within ParaView. So that's basically my introduction for the course itself. And I'll start with the overview of visualization. So maybe some background. The course that we're giving now is a bit of an extension and slightly different one than we usually give for University of Amsterdam, for example, where we have both scientific visualization and information visualization as part of the course, not just ParaView. And this next part, this visualization overview, comes from that course. But I thought it would be good to still include it, give a bit of background into what the different visualization types. So to start with a very simple example, maybe you've heard of this thing called Anscombe's Quartet, which was a paper already published a long time ago in 1973, where there was a statistician that, well, basically said, well, you need to visualize because statistics alone isn't good enough. So the quartet is 4 very simple data sets, XI pairs, A, B, C, and D. And when you look at these numbers, you can obviously see that there's, well, there's different values there, there's different patterns. However, if you then start to statistically analyze these 4 data sets, you get the same values, for example, for the mean and the standard deviation in X and in Y. And if you apply a linear regression to these values, you get basically the same expression for all of these 4, kind of suggesting that these data sets are very similar. But then if you visualize them, so we plot here these XY pairs as points, you can see that they're very, very different, even though the statistics suggested that they are not. Right, so visualization is an added way to analyze your data next to the statistical methods. And it can really help you to, well, to see the data literally, of course, but also to get an intuitive feel for what is in your data set, for certain patterns that are there, that are very difficult to do when you do just statistical analysis. And then a couple of years ago, some people from Adobe, I think it was, took this a step further, and they created a method to basically generate any type of data set, maybe even looking like a picture, where these statistical values are predetermined. So you basically have an algorithm where you input these means and standard deviation values that you want to have, and then it generates a data set that adheres to those statistics, even though it's just a very, well, it's either a random set or based on a picture. So this just reinforces the whole idea that statistics alone isn't good enough. So in general, the reason that we see for visualization, apart from the statistics part, is that visualization is a very intuitive way to see patterns or anomalies. For example, you might be working on some kind of HPC simulation, and you think your code looks good, and then you run the code and you look at the output files and think, well, that's fairly reasonable. But then you load in one of your snapshots into, for example, ParaView, and see that there's very weird things going on. That might be a bug in your code, or it might be a bug in the algorithm, or something like that. So this type of checking of your output can be a very, well, low-hanging fruit way of doing that. Another nice thing about visualization is that you can take the data or your simulation that you have and place it into a broader context. For example, you can show your simulation data and then add a few relevant 3D models, or maybe a background image or something like that. And that can be a very attractive way to communicate what you're doing, what your research is about. And of course, visualization can help very well in discussions with your peers or colleagues to see what you're working on, what the results are, etc. So here's an example from the Netherlands. Two images. One is the votes for a certain political party in the country. So you can see this strip within the country where there's a lot of votes for this party. And over here we have the vaccination percentages within the country for each of the counties. And you can see that there's, well, definitely some correlation. This strip for this pretty conservative party also has a fairly low vaccination rate in more or less the same areas, but that's not the whole story, right? There's also other areas where there are lots. Now I have to move. How do I do this? So when we look into a more higher level classification of why you want to use visualization, the first one is the most obvious one, is to support your research activities. And I suspect that that's what most of you are interested in, where you use visualization within your research, within your workflows to visualize the data, to look into data sets, to check for mistakes, etc., or to communicate. The second use for visualization is for PR and communication purposes. And the reason for classifying this as a different use is that you usually need slightly different visualizations. For example, pictures that look a bit more attractive, more realistic, that are less abstract than the usual scientific visualizations that are very much geared toward analysis, that tell the scientist something, but maybe not the layperson. So you might use such images, for example, in journals or in posters, proposals for new funding, or social media. And here the goal is really to get noticed, to engage your audience, or maybe to tell a story. And then a third use that we use ourselves quite a bit is to just have a bit of fun, either with a data set or when you're stuck in a project, is to make something interesting. For example, here is a red blood cell simulation that we worked on at some point, which at some point I turned into these minions. So this is simulated data, but then added the glasses and the yellow stuff, etc. Just because we were more or less stuck in handling this very large data set, and I wanted some relief, basically. And another more creative use of visualization was where we a simulation from the University of Twente, which is a very fundamental turbulence simulation, and then 3D printed it. You can see a keyboard over here for scale. So this was quite a large 3D print. Normally, these researchers would just analyze this type of data, visualize it on their screen in ParaView. But by turning into something physical, which we use ParaView for partly, it became a very interesting exercise to see if that added something to the feel you get for this data or the analysis that you do. So I guess the message for this one is it's okay to just play around a little bit with visualization, because it is a fun thing to do and it's very intuitive. Some example of what you can tell a story with the visualization. Here's something that some type of data that was plotted over time, as you can see, from the 1930s to the 1970s, more or less. There's different categories. I've hidden those categories, of course. And you might not exactly know what this data is about, but if you just look at this timeline as it is, you can definitely see that something happens roughly over here, right? Even if you're not a very skilled researcher or a lay person that doesn't really have something with science, something is going on here. And in this case, this was the introduction of the polio vaccine in 1955. You can see that this visualization really nicely showed that the effect of this vaccine after it was introduced, where the number of cases of polio dropped dramatically after the vaccine was introduced. And this graph was actually retweeted by Bill Gates because he thought it was such a very good example of visualization in action, where really say, well, something happened, we introduced the vaccine, and there's the effect. But you can see, especially in the news these days and in different social media channels, there's a lot of things going on where people abuse basically visualization because it is such an intuitive thing, and people see a graph and think, oh, it must mean that. So here's an example from the Financial Times, where the story that this graph was part of was that the US dollar as a reserve currency was declining in importance, which is what the light blue line shows. So it's the percentage of foreign currency reserves going down from roughly 75 to 60%. And then very sneakily, they added a line for the Chinese renminbi as well, which seems like the Chinese coin is now almost on par with the US dollar. But if you really look into it, the US dollar uses the left value scale, while the Chinese coin uses the right value scale. So it's not even close. And then when you check the numbers, in, for example, Wikipedia, you can see that it's only 2.7% for the Chinese coin versus 59% for the US dollar, which is what this graph shows, just in a very sneaky way. Now, people don't always do this on purpose, of course, but you can also make accidents when you're visualizing by, well, the way that you plot or the way that you show things that people might misinterpret because they don't fully understand the visualization method, or something is missing in the legend or something like that. When it comes to types of visualization, we basically use two main classes. One is scientific visualization, where you have data that has more or less a geometric structure or is some link to the spatial dimension or to reality. And the other one is information visualization, where you have data that's more of an abstract nature. For example, a table of numbers, the numbers over time, as I just showed them. And I'll have some examples further on. And then there's a process called visual analytics in the literature. It's where you basically work on analyzing data using visualization and a human in the loop to drive discovery, to drive exploration. So, definition of scientific visualization. I'm not going to read it, but it's about visual representation of data sets, usually from scientific experiments or simulation. You want to get a deeper understanding out of this, or a simpler representation of a complex phenomena. One of the scientific visualization that you see a lot in the news these days is, of course, related to climate change. So here's one from NASA using I think simulation based on atmospheric computations. You can see, due to the color scale, that over time Earth is slightly warming in this simulation. And well, people have been seeing these types of visualization, of course, a lot, especially in the last, let's say, 10 to 20 years. These red colors being shown everywhere as a warning. You can start to question is how effective is that still to show these types of visualizations. But for scientists, of course, this is the main way to visualize this type of research. And this is a scientific visualization because if you simulate, for example, the Earth's atmosphere, then you have a spatial representation. You have a 3D model, basically, of the atmosphere that you can then map into a spatial, an image, basically. Other types of scientific visualization are more in the medical domain. For example, output from CT or MRI scanners. With those, you can always produce very nice scientific visualizations using a technique called volume rendering, which we'll show later. But also, for example, brain imaging is where you have well, the different slices from the brain. Those images by themselves already have the layout of the brain, which they follow. And then showing those types of those data images on top of, for example, brain slices is a very nice way to visualize the data. And it's basically the only correct way to do it, because you need to align the data slices with the actual brain slices in order to interpret the data. So again, it's an example of scientific visualization. An example from NASA, basically the airflow around the landing gear of a Boeing airplane in very high detail. So this took a lot of HPC resources to compute this visualization. And here they use a technique called, or at least a mathematical construct called the Q criterion, which is related to turbulence and vorticity within such simulations. What this shows is how air that, well, basically encounters the landing gear ends up being very turbulent when it passes it. And it would actually be pretty hard to analyze these types of flows using just statistics, of course, right? You need these types of visualizations to understand the vortices that are going here, these rolling patterns, or the very minute turbulence structures that are there. So here it's just essential to do the visualization like this. But even when you have the spatial layout given basically by the data, when it's defined like that, let me move it here. You still have quite a bit of choice in what type of visualization features you're going to use. So within the hands-on later, you get to try a few of these. So for example, there's glyphs, is where you use very small and simple 3D elements to show, in this case, airflow direction and airflow magnitude. But you could do the same thing with something called streamlines. It's where you let virtual particles follow the flow from the simulated airfield, from the simulated data set, which gives you a very different view of the same data. Or you can use volume rendering, we already saw, where the light blue color means that the airflow is relatively slow, or different ones as well. So one of the somewhat challenges when using a tool, for example, like ParaView, is to figure out what is a good visualization pipeline, what is a good visualization set of methods for your particular data and for the type of analysis that you're interested in. And luckily, ParaView makes it quite easy to experiment and to switch between these different types. Small intermezzo on color scales. You might be familiar with the default rainbow color scale that is still used in a lot of packages, or a grayscale. However, ParaView chooses a different default. It goes from blue to white to red, where white is more or less the middle of the data range, blue is the lower end, and red is the higher end. And the scale is set up in such a way that it is a perceptually linear scale, which means that the colors by themselves don't really indicate certain patterns in the data. They try to be neutral in that respect. And you can see that very nicely here. So this is 3 times the same data set. When we show it in grayscale, you get almost, well, no pattern other than the horizontal and vertical regions that are in there. When you show it in the ParaView default scale, you can see that there's these peaks here of higher values. But if you were to show it as a rainbow color scale, you can get these, these edges that seem to be very pronounced in yellow, which seem to suggest that there is more structure to this data than there actually is when you look at it in these color scales. So the conventional wisdom these days is that the rainbow color scale is not a really good color scale because of these effects, and it's better to either use grayscale or a perceptually linear scale like this. And ParaView is basically doing the right thing there. So this is the default scale. You can still change it if you want to, but it's just normally best to just start with this and then tweak as necessary. So that was scientific visualization. Then we go to information visualization, where you have abstract concepts and relationships that do not immediately have a spatial way of showing them by themselves. So you need to choose that in that case. So here's an example. This is called the billion dollar ogram. It's a little bit older data set, and it shows the different amounts of money spent to certain categories by the world. For example, the US defense budget in that year was $726 billion. The cost of the Iraq and Afghan war was estimated to be $3,000 billion, etc. And you can split up all these different categories and put them in this graph like this, which gives you relative sizes and relative importance of the different costs. But the nice thing is you can also make comparisons then. For example, the worldwide cost of the financial crisis was the same area. So it's the exact same amount of money as all these different categories combined. So in this way, instead of having a table with these numbers and saying, well, this number is the same as all those other numbers combined, you show them as a picture. And for certain cases, for certain types of communication, that helps a lot. When you have graph data, so relations between entities, visualization is usually, it's very important to do it to understand the graph structure, but it's also tricky because since there is no natural way to show a graph, basically, you also always choose a certain algorithm or a certain layout yourself. You might introduce effects in the visualization, or at least suggested by the visualization, that are not fully supported by the data. So here's an example from the University of Amsterdam. This was research where a group of men in Italy was followed, was interviewed, and this was research into the sexual relationship, homosexuality, and the behavior in number of partners and such. And each dot within this graph is a person, and the link between persons is based on sexual partners and the number of partners that they had. So that's the data set itself is a graph. And then if you plot this graph in a layout, it falls apart in this case in more or less 3 groups. And the difference is whether they're homosexual or heterosexual. And a third group, which I don't fully remember what it was. But the point here is that within this group over here, you can see the color seems to suggest that there is like a gradient. So the color is I think it's the date of first infection, the HIV virus. And you can see that there's a layout from, well, 1990s all the way to 2009. However, when they look into this data, this pattern is there, but it's not as pronounced as the visualization seems to suggest here. And that's because this graph layout is based on forces acting between these particles. So it's literally a 2D algorithm. If you have a link between particles, they attract, etc. And this structure comes out. But if you use a different layout algorithm, then you would get a different layout and a different suggestion for the interpretation of this data. So graph data is especially tricky to interpret visually. Fairly well-known very well-known information visualization was done by Hans of Rosling. He even made this movie about it. And what it shows is the evolution of countries in terms of GDP and expected lifespans of people over time. So this starts in the 1800s, where life expectancies are fairly low. But as time goes by, you can see that certain countries start to rise when it comes to life expectancy. You can also see that the average income per person rises when it goes to the right. And then the size of the bubble shows the population size of the country. So this is a very nice interactive, well, it's not interactive, but animated way of showing patterns in this type of data. And the way he tells this story is also very interesting for, let's say, the layperson or as a newspaper or news article. But this is it's made possible basically by being able to choose your visualization type and your representation when it comes to information visualization. So a particular class of information visualization is geospatial visualization, because there you are limited usually by a map that you have to use, because the data that you have is related to, for example, counties, in this case in the UK. So you have to put the data where the data is, basically, but you still have somewhat flexibility in tweaking that map into something else. So here, these colors are related to the amount of wealth distribution or wealth equality within different regions. You see that a lot of wealth is concentrated in the London area. However, London is very geographically is very small, of course, compared to the whole UK. So what they did in this case was to normalize the map based on the amount of people that are living there. So then, of course, the London area becomes much larger because of population size there. And it gives a better overview of wealth per number of persons, basically. So this is the real map, and this is then the tweak map. And that's the flexibility that you have in this case. And then finally, there's a class called infographics or information graphics, which can be any type of visualization, but it's usually an image aimed at the layperson. It's an attractive image. You don't have a lot of text. You just have maybe a legend or a few sentences, or in this case, things pointing out things. So this is a map of the Netherlands, the population density per county. The higher the piece of diagram, well, the denser the city is. So Amsterdam here is a very high density region. As an analysis tool, of course, this is not very good because you can hardly see the data that's behind these bars. But it can immediately suggest a certain story to the person that is viewing this image. And you can do the same type of visualization with scientific data as well, right? You can try to make an infographic for your research to see if that helps in communicating it or promoting it. Some slightly more scientific subjects. On the right, we have the fate of different Mars missions. They send over time different probes to either get into an orbit of Mars or to land the lander there. And this is from the 1960s until basically 2010. And the ring where the mission ended up is how well the mission went. So the first ring is the mission failed. The second ring is there was a flyby of Mars. The third thing, it went into orbit, etc., all the way to landing on Mars. And as you can see, over time, things got better. Right? The missions were more successful. We managed to land on Mars, etc. So this is a very attractive way. Again, you could show this in a table or as a large bunch of text describing this, this history. But this is a much more attractive way of showing it. And then on the left side, there was at some point an Indian Mars mission, and the story there was that it was very cheaply done. So it's over here, $74 million for this particular probe. And instead of showing just other probes that were much more expensive, they also show a number of movies about space exploration, just to show that the movies were more expensive than the probe, which is kind of a nice story. So very simple visualization, but with a tongue-in-cheek subject. And then finally, I mentioned this idea of visual analytics. We start with data, you map it into a visualization with user interaction, for example, to learn about the data, to gain knowledge. And then based on the knowledge, you can either tweak your simulation, for example, or your analysis methods, make new visualization or make new models, and etc. So this whole process continues, and it's basically something that you do implicitly anyway in your research, I suspect. But there are tools that are aiming to facilitate such a visual analytics loop in very specific ways, where you structure this whole process more. And ParaView is a tool that you could use, especially for the visualization part, but also for the analysis part a little bit in a process like this. Okay, so that was basically a short overview of different visualization taxonomies, basically. So scientific visualization, the one we will be focusing on mostly right now. Information visualization is there. Actually, within ParaView, there's some possibilities to do things like histogramming or plotting lines. It's not very usable, but it's there if you need it. And when it comes to geo-visualization, ParaView hardly has any support for that because it doesn't know things about maps or projections that you usually need. And then for infographics, you could use ParaView. It has some options to produce somewhat nicer pictures. I will go into that later. I'll show some of those. And you can use that as a basis for an infographic, just to make one nice picture with a bit of text and a legend, etc. So I think one of the things that we always say is that you need to try to adapt your visualization to your goal and your audience. So here's an example. It's 3 times the exact same data set. It's a simulation of air bubbles within a turbulent flow by the University of Twente. On the left, we have loaded this data into ParaView, and this is colored based on the velocity of the bubbles. So it's a very straightforward visualization as you would use this in scientific analysis. Then in the middle, we loaded the same data, so these bubbles that have a color into to Blender, added a bit of a background, added some lighting, some shadowing. This looks a bit nicer, so this was made for a poster that we wanted to have on the wall. The left side, that would not have been a poster, right? It's just not, it looks not good enough. So we wanted something more. And then on the right side is a still frame from an animation. So the simulation is obviously time based. And then we rendered these time steps into a very nice bubble-like surface. It really looked like air bubbles in water, and put that on a large screen on a booth to show the research in action. So you can really choose how you'd like to visualize data like this. And depending on the audience, you might choose something like this or something like this or something in between. And it's really up to you what fits best or what you have time for, of course. In general, we do find that aesthetics matter a little bit. So it looks nice and people are more likely to look into it. And that might be something that you want. Then you need to do visualization, of course, using some type of software. There's an enormous amount of packages out there. We focus on ParaView here, which is based on VTK, which I'll show later. But there's others. There's Visit, which is more or less the arch enemy of ParaView in certain respect. It's from a different set of labs in the US that built their own visualization tool. It's very similar in what it can do, but the interface is very different. But these days, there's also something like, for example, IPyVolume, which is a library that you can use in a Jupyter notebook to do the type of visualizations that ParaView can do, but then within the notebook and interactively as well. So if you like Python scripting and working in Jupyter notebooks, you can take a look at IPyVolume instead of using a tool, for example, like ParaView. And then for information visualization and medical visualization and other domains, there's very many domain-specific tools. You probably know at least a few of them, for example, Matplotlib or R. ParaView is very domain generic. It doesn't pick any particular domain to focus on, just basic scientific visualization. So I already mentioned VTK. So this can be interesting to if you want to build your own pipelines on a very low level. So VTK is a class library. It's basically 1,500 C++ classes that do things like visualization operations or extracting a service from a data set or turning one type of data to something else. It's been around for ages. You can use it either from C++ or for Python, Java, and a few other languages. And you'll have to program, but it's very much what ParaView provides in a GUI, but then as a programming library. So since ParaView is based on VTK, that makes sense. VTK works on the concept of a pipeline, which I'll go into a little bit later. This pipeline then turns data into something visual, and you can either render that on your screen interactively, or you can save it to an image. But here we'll focus on ParaView. So this is the snapshot of the ParaView user interface. You can see the data as you work on the pipeline that visualizes it and change parameters, etc. Okay, so that was an introduction to visualization. I'll next move on to diving into ParaView a bit more, unless there's any questions at this point. Oh, somebody is watching the chat. If not, I'll continue. So more details on ParaView. So as I said, ParaView is a generic scientific visualization package. It's not tied to a particular domain or scientific field, but it works best for 2D and 3D datasets. There is support in principle for 1D datasets. If you have that type of data, it's not very interesting to visualize with a ParaView, I would say, but it's there. And if you have an animated dataset, so something that has time steps as the simulation progresses, then there is basic support for that in ParaView. So you can load in these snapshots of your simulation and then apply the same pipeline to each time step and go through the simulation over time by playing or rewinding to the beginning, etc. Or render an animation movie. As I said, ParaView is not strong in any particular domain, but it also doesn't try to be. It just tries to be generic. But depending on the domain that you're working on, you might hit upon limits that are not taken care of in ParaView, or your type of data isn't fully supported in the way that you'd like to. So ParaView is very good at interactively and exploring data and doing visualization of that, because that's what its main purpose is. It can be quite a joy to work with when you build up pipelines and you quickly have the visualization that you were intending. There's a lot of operations and different types of visualization methods in there, so it's quite capable in that respect. Sometimes you might load data that isn't fully processed yet. You might want to clip away a part or compute some statistical operation that you'd like to do in the visualization. In many cases, ParaView will have a filter for that, so that saves you having to script that separately as for example, a Python script. So look into all the different filters that are there. There's quite a lot of them. And obviously, when you want to have your own data in there, you need to convert it to the type of data model that ParaView uses. We'll go into that later. The data model is fairly comprehensive. It's also fairly clean, which is a good thing, but it might not always be the most efficient data model when it comes to memory usage or applying operations to the data in that model. And again, we'll look into that later. Some of the things in ParaView that are, I would say, okay, so not perfect, but usable. You can render images from ParaView into a separate image file with a few clicks of a button, which is okay. You know, if you have an animation setup, you can render that to a video file. There's quite a selection of data types or file formats that it can read. However, sometimes you might have a file that reads in such a way that it's not entirely, that it doesn't pick out of all the data that's in the file, and that doesn't end up in ParaView, for example. Or it might not read a particular type of file that you have. So sometimes you might have to work on pre-processing your data into a different file, or maybe even extending ParaView with a script or a plugin to read your particular data. ParaView has Python scripting, so you can script various things. For example, you can write a whole workflow where you read data, visualize it, and then write it to an image file. Once you have that script, you can then apply it to different input data, for example, to render the snapshots of your simulation. It's quite okay, it's usable, but the API is a bit hard to get into. And I'll show that at the end of the course today. Something that's very interesting is when you have a very large data set that doesn't fit, for example, on your laptop or on your single HPC node. And ParaView offers a parallel rendering and parallel analyze mode. So you will have an MPI, set of MPI processes running on multiple nodes, usually using multiple GPUs as well to do the rendering. You can still use the regular ParaView GUI to connect to those MPI processes. and all the parallel processing is happening in the background. You don't really have to worry about it, while you can still use the GUI in the way that you normally do. So this is a very powerful way to work with very large data sets if you need to. But it's like I said in the slide, it's a bit of a beast to use. It can easily crash. It's somewhat hard to set up correctly. You need to tweak your data files to be in the right format. But sometimes that's the only way that you have to visualize these very large data sets. So we show it at the end a little bit. And then there's some things that are really, I would say, questionable in my mind. There is some statistics support within ParaView for information visualization, or even loading in geographical style data. I'm not entirely sure why it's there, because it's either not very powerful or it's buggy. So you might want to avoid things like that. Then one question you might have is, why would I use ParaView? Well, it's free and open source. It's been around for ages. In 2002, when the first version was released. It's actively developed by a company called Kitware, which is a US company. They take a lot of grants from US labs or the National Science Foundation. And that's also the reason that I like to mention this, is that it's not a commercial company building this product. So ParaView is really geared towards what the researchers and the grants that come in, what they want and what they need. Even though there's regular releases once a year, it sometimes feels a little bit like they're running one direction in this release and then running another direction in the way it develops. So it's not as polished as you might expect from, let's say, a commercial product. That being said, it's still a very good visualization package, I would say. Right, a lot of file formats are supported. So here's the list of current file formats, and then there's plugins to add a few more. So for example, OpenFOAM, it's an often used CFD package. It has direct support to load OpenFOAM files. Fluent is another one, and then there's a whole bunch of other file formats that just work out of the box in most cases. And there's also these different operations that you can do, which you don't find always in other visualization package. So it's very flexible, and it allows complex pipelines. There's a nice online forum called discourse.paraview.org. So if you have any questions, you're stuck with whatever you're working on, you can ask it there. There's a lot of the developers from ParaView there that are hanging out at that place, and they will answer you usually very quickly. Sometimes they'll say, well, sorry, that's not supported, because again, that's the way the ParaView is being developed based on the needs from a certain type of grant in most cases. But all in all, I would say that the ParaView is well supported. It's being actively developed, so it's a good basis to learn for doing scientific visualization. So the GUI and the workflow are pretty good for building up interactively and then seeing the results, especially for a course like this as an introduction to ParaView. You also get an introduction to scientific visualization methods and approaches, which I think is very valuable. And whatever you learn in doing ParaView, you can easily transfer that to other packages. For example, VTK has the same isosurfacing algorithm, but that type of isosurfacing is also in other packages as well. So whatever you do in ParaView, you can easily transfer that. And the scriptability in Python is usually a good thing for scientific workflows as well. However, it's not all 100% great. It can crash easily. For example, when you run out of memory, which might happen when you, for example, do the wrong operation on your data, causing data explosion. There's no checks on going out of memory. It simply crashes when it goes out of memory. So that's something to keep in mind. Certain areas or certain filters are a bit buggy. You can be pestered with a lot of error messages while you're working. And there's other limitations that you will encounter. So one advice here is to save the state of ParaView often when you're still trying to understand what is and what isn't possible, or if you have a system with not too much memory, because you might lose your work if you're not careful in that respect. And I'll show later how to save this data. So one tip for now, I'll put this in the chat as well. Is we have a link on a share online where there is the data files for ParaView. Open that link. So the core data zip is over here, which isn't too big. It's just a couple of megabytes. So these contain the data files to use in the exercise later. The slides are there. I still need to update these to the latest version. So I'll do that at the end of today. And then you will need ParaView on your system. So we provide binaries for the latest ParaView version for Linux and Windows here. For Mac, there's simply too many different variants when it comes to macOS version and signed or unsigned, etc. So you better go to paraview.org and download it there. And the reason that we put it on this different share is that the download from paraview.org is for some reason quite slow for me always. So it might take a bit of time to get it from there, and you can use our share instead. So my suggestion is to start that right now. Where is it here? Again, the link is in the chat. And then I'll continue. So the central concept that the ParaView works on is this idea of a visualization pipeline, which is, I think, very natural. So you have, for example, a data file or a set of data files that you load. You apply a number of operations to the data to get closer to something that you can visualize. And then the last step is that you put that image onto your screen. So it's a set of operations. In this case, we have a set of DICOM files, which is the file format that comes out of medical scanners. You read those DICOM files. These are the slices, in this case, from a CT scanner. The reader will then put those slices on top of each other, so you get a 3D volume or a 3D grid. By using what is called a contour filter, we extract a surface for a particular value. So in this case, we extract the skull or the bone from the scan data. Then apply a filter that's called clip, which simply removes part of the data. And then the final step is mapping and rendering whatever is in memory in terms of data onto the screen into an image. Well, that's a very straightforward pipeline. And then guys called Haber and McNabb in the 1990s formalized this a little bit in a paper, where they say, well, we have a number of data sources. It could be a file or a database. We have a number of filters that operate on that data that basically produce new types of data sets or part of the data. And then to go from data to something visual, we use something called a mapper or a mapping step. And that could be creating visual elements like a surface or a bunch of spheres or lines, etc. And then the final step is to take these mapped visual elements and render them on the screen, which could be, well, an image, or it could be a file on disk, etc. And the reason for mentioning this particular terminology is that ParaView and VTK use the exact same terminology. So you see a source, you see a filter, you see a mapper, a render. So in case you're wondering where does that come from, it comes from here. Just to make it a little bit more concrete, here's an example from the University of Amsterdam. It was a simulation of red blood cells. As you can see, these individual cells are modeled in such a way that they can stretch, they can bend, they interact with each other by pushing against each other, etc. Within this simulated blood flow, there's also an object, a stent, which is not visualized, but it's there. As you can see that the cells move around it. And then something else that isn't shown explicitly is that there is a fluid simulation underlying all this. So that these cells are behaving within this fluid. That's another data set that is being part of the simulation. So if you want to load this particular simulation in ParaView, it could look something like this. So over here, we've got the different files from disk. So the red blood cells, the fluid simulation, the platelet cells, which are these yellow ones, which are a different simulation layer, basically, different cells. And then finally, the static stent from an STL file, which is a file that contains 3D geometry. So we load that in. For the red blood cells, we apply a clip filter. So we cut away the top half of the cells, basically. For the fluid, we have two ways to visualize that. We apply a slice within the fluid flow, which is over here in the back. And we color this slice based on the vorticity of the fluid simulation. But we also apply these streamlines, which I mentioned earlier. You let virtual particles basically travel along the flow as a different way of representing the way the flow goes around this stand. And then we also apply coloring to the red blood cells to show the velocity. So you can see that the cells that have to move past the obstacle at this point have to travel a little bit further, therefore they need to move faster to keep up with the rest of the cells. So all in all, even though this is a fairly complex simulation when you look at it from, for example, the mass being applied or the interaction between the different parts of the model, visualizing this is, well, can be done with a small pipeline, not many filters. You just load in the different sources and apply the filters that you need. You pick the representation of the different types of data that you need. And ParaView already provides a very nice visualization that is still interactive, right? So you can, I'll show that later, you can rotate this, you can add and remove part heights, etc. So looking a little bit more into to what does a ParaView pipeline look like. So it's a data flow network where with the sources of the data are the files that you load from disk, or there's also some sources built in. For example, if you need a plane with a grid of points, you can generate it and then use that in your pipeline. Filters operate usually on one input dataset, but some of them have more datasets that they use as input. They always produce a single output dataset, and the way that it's implemented in ParaView is that if data from upstream filters can be reused or passed on without having to operate them, then it will. So there's a bit of caching going on there, if possible, in order to optimize memory use and not compute too much. Almost all filters have parameters that are shown down here. So for example, with the stream tracer filter, you can control the different integration properties, like the algorithm to use or the step length in order to do this tracing. And as you change these parameters, you can see the effects that this has on the visualization. It's important to know that filters usually accept only a limited type of data from the upstream inputs that they use. So for example, if you have a file reader that reads 3D points, so it's only points that you have in the dataset, and you cannot do surface smoothing on that. So the surface smoothing filter will simply not accept this connection because it doesn't know how to handle 3D points. And that's something that you can encounter in the ParaView GUI. You see a filter that is grayed out in name and you cannot select it. That's usually because of a mismatch in data type. And another limitation is that that loops are not allowed, so it must be a directed acyclic graph, this pipeline, which makes sense. And usually you don't want loops, sometimes you do, but it's simply not possible. Okay, so enough talk in slides. Let me switch over to ParaView itself. Any questions at this point in the chat? It looks actually. Okay, no questions. Good. All right, so I'll show some examples of ParaView in action. I'll load in a data file. Oh, still got something in the out. By default, you will get an outline of the data. So this is the spatial extent of the data. And here under this information tab, for whatever filter you've got selected, you can see the properties of the output data of that filter. So in this case, I loaded the .vtk file. This is one of the native file formats for ParaView and VTK. It tells me that the type of data is an image, in this case, a 3D image. So it's 128 to the third cubed. So when we change the representation, for example, to surface with edges and zoom in a little, you can see the different grid voxels within this data set. Right? So there's 128 voxels in this direction, this and this, and that makes up our grid. Now we haven't even looked into what this data set contains, but this already gives you an idea of the structure that it has. There's a few more statistics here, so it tells you the amount of memory that's being used for this data set. So it's only 8 megabytes, which is not surprising. It's a very small grid. It tells you the XYZ bounds, so the size in XYZ, spatial extent. And there's something called cells and points. And we'll go a little bit more into that after the hands-on when you talk about the data model. But this tells you the makeup of the data in terms of the ParaView data model and how many different types of points and cells there are. Or actually, the number of points and cells. So this is the default 3D view for a data when you load it. Now you can change the view by either hiding it, creating a new view, or splitting it. I'll hide it in this case. And then create a new type of view called the spreadsheet view. And this gives you a low-level overview of what's in the data. So really the data set points and the data set cells. So you can see here each point in the data set has got an ID, an integer, the structured coordinate, so it's the IJK index, and then the associated data density value. So down here, for whatever filter you've got selected, it will list the data arrays that are associated with the points and cells in the data set. So in this case, there's only a density value. It's a floating point type, and the data range over the full array length is 0 to 5, basically. And when we check the data values over here, you can see the individual values per point. We can also look a bit closer into the cell structure. Once again, I'll go into this later, but right now for a structured grid like this, all cells are of type voxel, which is basically a very small cubical element that contains either a value, or it might contain a vector, or it might contain a tensor or something like that. Great. I can switch back to the render view. So the default 3D view. Try a different representation. So we can switch from outline to something called volume rendering. And now we can see a little bit more of what's here. So this is, well, you can't maybe not tell from the data, but it's a cosmological simulation used with a couple of million of mass bodies that interact using an n-body simulation, and then they clump into these high-density clusters, and you've got these, well, linear filaments. And all in all, this is a very pretty data set to look at in this volume rendering mode. So we might want to say, well, we'd like to cut away half part of this the data set to see what's inside. So for that, we can use a clip filter. Up here, there's buttons for often used filters, for example, calculator, contour, or clip. When we add a filter, it does not immediately get executed, because filter execution might take, depending on the data, a lot of time. Or you might want to set a number of parameters first before you apply the filter. So by default, when you add a filter, it's not executed, and it only happens after you press apply in ParaView. So when we apply it, we now see that we have somewhat confusing view maybe, because what happens is both filter output is now visible, which is shown by these eyes here. So we might hide the original dataset we loaded and only show the clip filter, and now we get at least only part of the visualization, part of the dataset. We hide plane here, then that leaves out the clipping plane that you can interact with. And it's a bit of a weird view of the same data we just had, because now this seems like a block of data. And what happened here is that the representation changed to surface. So we can switch back to volume. Might take somewhat time, because what has happened now, you can see there's a different behavior now when I interact with it. If you look at the information tab over here, the interface is also quite slow now. The data type changed to an unstructured grid, while the input data was a grid, a 3D grid, an image. So some filters, in some cases, will generate what is called an unstructured grid. And this is basically the worst type of data set within ParaView, because there's no optimizations in terms of the way the data is laid out in memory. It's really just a list of individual voxels in this case. And that's not efficient to render or to interact with. So depending on the operations that you do, you might encounter this type of grid. So because the interface is now really slow, I'll remove this one. Let's try a different filter, an ISO contouring filter, which is this button over here. And let's say we'll extract a value of 1 by the original input. So what this has done is extract a service that follows a specific value within the data. So the value is 1, and you can see that there's lots of services, lots of areas within the data set where this value occurs. But we could decrease it. Let's say we are only interested in density 5, so high density. Did that show anything? Let's check the information. So what came out is a very small number of cells, so just 16. It is there somewhere. We can't see it. So let's try a different value. Let's try a density value of 5. And now we can see a little bit better that there are these regions within the data set where this density of 4 is occurring. Now we're a bit lost because we can't see the outline of the domain. But it's actually a simple way to add that. So show the original data set to change its representation to outline. We always get the context of the full data domain. So even if you're not entirely sure where the data of a filter, for example, contour is within the domain, by showing it explicitly like this, you can still get that context. Okay. So as you can see, it's very easy to switch between the representations or to work with this pipeline like this. Let's try something else. So we now have one representation, but we, for example, might want two side by side. Well, that's possible. Up here with this button, there's a way to split the view into 2 views, which can even be of different type. We'll create a second render view here. Let's show the contour here, and we'll do volume representation on the left side. Let's tweak this contour to be a little bit more interesting. So prepare it 2.5, get a few more clumps. So now we have the same data, different representation side by side. This is almost perfect. And the one thing that we'd like to do is to link the camera views between those two. So we can right click in this area, pick link camera, and then click on the view you'd like to link. And now when you interact, you always get the exact same camera view when interacting. And this can be a very nice setup. For example, when you want to compare different parameters or different time steps of the same simulation side by side. You can split further. You can have 3, 4, or more areas like this. So as you can see, it's very flexible in way that you use these layouts. If you like to add one, you can even add a complete, oops, that was the wrong type. Like a render view, and then do something else here completely while you still have your original layout here. So the interface really supports you when having different variations or different analysis of the data. There always is a single pipeline though, so you can only choose what you see within the view based on these icons here, but it's always the same pipeline. Suppose we wanted to save a screenshot. That's very simple. File, save screenshot. We'll save it. Name. Okay. Yes, place. And then it gives you some options for the resolution, or maybe you'd like to change the colors or things like that. Now it's saved to disk. And there it is. And you can do all these steps from Python as well. So I'll show that later, but basically what you do is you trace, you start tracing the Python steps. You do the things in the user interface that you like. You stop the tracing, you get a Python script for whatever you were doing. That's a very nice way. Okay. Yeah, I want to show one more thing. So as I mentioned, there's very rudimentary information visualization or analysis tooling. For example, I can apply a histogram and you get a plot like this. You can change the bin count to get a little bit more detail. So that's one way in which you can get some kind of a statistical overview for your data. Another option would be to use a plot over line filter. What that does is it allows you to indicate a line, start endpoint. For example, I've got it across the full data set right now. And then it shows you the values that line encounters over as it goes from one point to the next. Right, so we've got high density cluster being encountered over here somewhere. That's this peak in the graph. So these types of analysis could be useful if you quickly want to check something about your data or not, without having to do a script in Python that you write with matplotlib, for example. Okay. Due to the time, I'll say we'll get started with the hands-on. So, as I mentioned, this is the same URL I showed earlier that's in the chat. Here you can find the binary, the ParaView binaries, the course data zip file. The idea is to install ParaView 512 on your laptop, download this course data, extract it somewhere. And then for the exercises, those are at a different website. I'll put that in the chat as well. So here you can find the exercises. There's a number of them. It basically goes through step by step what to do. So open a file, tweak a pipeline, check some output, etc. There's different types of data. So there's a CT scan of a boy where there's a bit of a what do you call it? An exercise to figure out what's wrong with the boy, why he was in hospital. We've got a tornado simulation that's in a CSV file, which presents its own type of challenges. And we have an example animation where you can just play around with something that animates over time. And then if you have time left or you'd like to challenge something, we have this bonus exercise where the goal is to recreate this picture based on a data file, and you have to figure out completely by yourself how to do that. So those are the exercises. As I mentioned, we have 90 minutes scheduled, but we're a little bit late. So I suggest we start again at 11:30. I'll come to the question. Let me just finish this. So start again at 11:30 with the slide presentation. Within the hands-on part, you can take a break as you like. We have breakout rooms in Zoom to have one-on-one interaction in case you get stuck. Maybe there will be more comments on that from IT for Innovations. Question from Parvin?
Can you hear me?
Yes.
Hey, Paul. I have one question. I'm actually working with a NetCDF file for my work. And I was wondering that if all these filters and all these features can also be applied to NetCDF files. And can I do the same for these files, or is it just for the BTK?
So NetCDF is supported in reading. However, because NetCDF is a very general file format, I found recently out with one of the researchers that we work with that the way that ParaView reads these files isn't always the way that you want to. For example, it might miss the structure that's in the data, or it might miss a certain way that the grid is set up. So the best way is to try it, but I suspect it will not do for you what you want to. And you either need to pre-process the NetCDF files or do something else. So NetCDF is very similar to, let's say, HDF5, which is also a very general file format for storing arrays. And then ParaView needs to be told basically how to interpret those arrays, and the same applies to NetCDF.
Yeah. Okay.
Yeah.
Okay.
Yeah.
Thank you.
Any more questions? If not, then yeah, good luck with the hands-on. Yeah, so I hope all of you managed to make it a ways into the exercises. The website will stay up, the data files are there, so you can continue if you'd like to. I was wondering if anybody managed to figure out what was wrong with the boy in the first exercise. Anybody find anything strange?
Probably a coin in the nose.
Yeah, you're right. So there's up here next to the right eye, there's what appears to be a coin. We actually don't know what it is. So this data set came with a paper. It does say that the boy was hospitalized for something, but not what exactly it was. And we've been trying to figure out what it is ever since. But indeed, that's it. Okay. Let's continue. So the next part is to look a little bit more into the way that ParaView represents data, because it is important if you're going to load your own file that you might have that might or might not immediately loads into ParaView, yes or no. You might need to convert that or not. There are a lot of file formats that are supported by ParaView out of the box. So I already mentioned OpenFOAM, NetCDF, HDF5, and a lot of others. You've seen in the exercise how you can get tables from CSV files into to ParaView. But it depends a little bit on the specific file format support if the reader that does the reading produces a dataset that is immediately useful, especially for these generic array file formats like HDF5 and NetCDF, because there is an infinite number of ways to interpret those arrays, and ParaView might not always do it in the correct way. So apart from using support for file formats that are there, you can also write or convert the data that you have into the native file formats for ParaView and VTK. There is a legacy.vtk file format, which is fairly simple. It is well described. There's also the newer file formats, which are XML based for some reason. So it's basically an XML text header and then a binary dump, more or less, of the data itself. And all of those are described in this link in great detail. So hopefully that should give you enough information. And the other option that I would recommend is to look into XDMF. So XDMF is also XML, but a lightweight file. And that XML file references an HDF5 file containing the actual data. And HDF5 is a very generic multidimensional array container, basically, where you can have many different arrays in one file and then reference them from the XML file. And ParaView has fairly good support for XDMF as well. But then, of course, the question is, how do you write the data? What format does it need to be conceptually in terms of topology and things like that? So when we look at the data model for ParaView, there's basically a single set of concepts that is used. It's all used by all filters use the same concepts. It's a very general and very flexible format. In most cases, it's reasonably efficient to operate on by these filters, but it's not the most efficient, because especially memory-wise, it might not be the most efficient way to store the data within ParaView, but that's simply the choice in design that has been made. So the nice thing is that it can represent all different kinds of data types and different types of models, for example, an image or a point cloud or a shell, a polygonal shell. And we'll look into a few more of those in a bit more detail later. So first, some detail on the model itself. So all datasets are represented by a mesh and attributes. And the mesh is made out of points and cells, and points are either 2D or 3D coordinates, and the cells are made up by connecting points. For example, here's a quad cell that connects 4 points, or a triangle cell that connects 3 points. And then the mesh is basically composed of all the cells together. Both points and cells can have attributes. For example, you can have a temperature or a pressure value at point locations. And then within the cell, interpolation will happen based on the corner values that are there. Or you can have values associated with cells. So you can have a pressure value, a single value within the cell, and a different value in the neighboring cell, etc. And then if any point ParaView needs a point or a pressure value, in this case for a point, it will interpolate based on the cells that point is being used in. So this is all fairly straightforward way to associate data arrays with a mesh. in a way that makes a lot of sense for scientific data and scientific simulations. So the filters in ParaView either operate on points or cells or both, right? For example, a smoothing filter that smooths out a 3D surface will use both the cells to figure out the connection of all the points, but also the point positions in order to create a smoothed representation. But another filter might only work on points, for example. And the important thing to realize is that ParaView only visualizes cells. So the points are more or less implicitly used. It only looks initially at the cells and visualizes those. And that also means that if you have, for example, a point cloud, which is only 3D points, you still need to create cells for each point. So you get a vertex cell for each point. I'll show that later. Here's an example from a CFD simulation of the wind flow around a set of buildings. This is one of the OpenFOAM examples. I've selected here part of the scene, just a few cells here in purple. And then on the right, you can see the details per cell that is selected there. So you can see the different types. So quad cells are 4-sided. We've got the triangles, a few of them. And the polygons are 5 sides or more. And then associated with each cell, you can see the different values. So you can see there's a whole bunch of values being produced by an OpenFOAM simulation. So there's velocity, there's pressure, there's other values as well. And these little icons here indicate if the data is associated with the points in the dataset or with the cells. So these are the point-based values, these are the cell-based values. And then using the spreadsheet view, you can look into these values as I showed earlier. There's a whole bunch of cell types, both in ParaView as well as VTK. They use the same collection. So some of the most straightforward ones are the pixel for a 2D image or the voxel for a 3D image. Right? So these are cubical elements that you can put a number of them side by side in order to build up an image or a 3D grid. If you have a voxel that is not entirely square, then it would be a hexahedron, right? We can be basically a deformed cube. And the different ones that are used within, for example, CFD simulation, like a wedge or a pyramid or a tetrahedron. And all ParaView datasets are made up of these types of cells, basically. And then depending on the specific class of dataset, certain cell types and certain topologies are allowed. So one of the most basic ones is this rectilinear grid, a uniform one in this case. So this is, you can see this as either 2D or 3D dataset that we've already used. So for example, the CT scan. The spacing is fixed within this type of grid. So it's for X, all cells have the same spacing. There's some origin point and there's some dimension in the number of cells in each of the 3 dimensions. And that in turn implicitly defines each cell to be either a pixel in 2D or a voxel in 3D. But usually in simulations, there are slightly different grids. So here are some of the ones that are supported by ParaView. So instead of just having a uniform rectilinear grid, this is a non-uniform rectilinear grid where the spacing can vary per dimension. But you still have rectangular pixels and voxels due to the way that the grid is set up. If you need something more flexible, it would become a curvilinear grid where each cell is either a quad in 2D or a hexahedron in 3D. Now here the topology is exactly the same as here in terms of which cell is connected to what. But the point locations can be flexibly defined by the user. So it's a slightly more flexible grid in this respect. And then we have grids that have varying levels of detail. It becomes an adaptive mesh, refinement mesh, or AMR mesh. We have a hierarchy of basically uniform grids. For some grids, cells are not subdivided, for others are more subdivided down and down. So these are basically the grid types that are supported by ParaView. Your simulation, for example, might use a cylindrical grid. There is no direct support for that in ParaView. So you need to convert your polar coordinates, for example, to one of the grid types here explicitly first. So those kinds of limitations are, well, important to keep track of when you start working with ParaView. For point-based data sets, for example, in body simulations or LiDAR or agent-based simulations where you have point coordinates, the support is there. You can associate, as already mentioned, data per point, for example, a mass or a velocity or a color or something. You still need a vertex cell to be defined per point, which is something that either the importer will do for you or something that you would need to do in the script, which isn't hard to just create one vertex cell per point. Polygonal data or 3D services are used quite a lot, of course, in all kinds of simulations. For example, this red blood cell simulation. That's basically a shell that can be deformed, which is made up of triangle cells. These services can be closed, they don't have to be. There's actually a sort of special case within the ParaView datasets is polydata, and these limit the cell types to these. So it's either triangles and quads within a mesh, or polygons when it's 5 sides or more, and then lines and vertices. And that completely defines 3D polygonal data. There's some importer support, for example, for the .pli formats and others as well. And a lot of the filters are specialized for operating on polygonal surfaces. And I mentioned earlier the unstructured grid. So this is more or less a collection, a list of cells that can be of any type. So there's no limits on that. Because it's a list, it's not very memory efficient because each cell is represented separately. Some filters produce this kind of data, and then that limits what further operations you can do on these unstructured grids. Because they are so general, not all filters can handle them. So an example is a CFD mesh when it's tetrahedral cells. These are individually listed. Yeah, and polydata is a form of unstructured grid, but it's not only stored more efficiently, but certain filters handle it more efficiently. So here's an example. Start with a wavelet, which is a 3D grid in this case of 21 cube points. When it's the output from the original filter, the wavelet filter is a uniform rectilinear grid. So it's stored very compactly, 37 kilobytes, which is just 21 cubes times 4 bytes for the floats. That's exactly 37 kilobytes. So that's really what ParaView is storing there. Now suppose that we execute a threshold filter to select part of the data, but in this case we select the whole data range, so the full wavelet. An unstructured grid comes out. The number and points of cells is still exactly the same. However, the memory use is increased by almost 20 times. And the reason for that is the wavelet uniform rectilinear grid implicitly defines where the points are, right? It's just this origin and then the step size and the number of values. While for the unstructured grid, each cell and each point is explicitly stored. So you get the point coordinates, which takes up a lot of memory, and then dividing each voxel explicitly in terms of points A, B, C, D, etc. takes even more memory. So for a small data set like this is not really an issue, although you might hit upon this limit that unstructured grids cannot be processed by many filters. If you start to use very large data sets and you apply an operation like this can really blow up the memory usage that you have in the application. Okay, so that was a bit of information about the data model. We'll continue with improving the visuals of your model. I'll do a short demo within ParaView, but there's also a reference in the course page that you've been using where the exercises are with more or less the same stuff, but then written down. So I've got the boy loaded here. I've got the ISO services extracted. I suppose we want to get a little bit more insight into the different structures that are here. You can look at it like this, interact with the viewpoint, etc. But it's actually quite hard to see the spatial relations here, the depth of certain elements, how something overhangs something else. So what we're really missing here is something like shadows or a more realistic representation or rendering of this data. In modern versions of ParaView, ray tracing has been added. So all the way down here in the properties, there's a enable ray tracing setting. You might not see much difference yet, but it is now switched to a different rendering mode. And then the next step I can do is to enable shadows. And that already helps a lot. So there's now a light source somewhere in the scene. You can see shadows being cast. For example, I can disable shadows. You can see the difference. And this really helps in interpretation of the data, of the spatial relationships between elements in the 3D model. But it actually makes the model itself more attractive as well. Because this is more of a realistic view of such a model. Now something has changed because I said the rendering mode changed. This is now using the so-called Osprey Raycaster. Osprey is a library from Intel, and because of this, it is CPU based. So this is all rendering on the CPU, and you can probably tell the interaction is a bit more sluggish now, which is a downside, but that's the way it is. But if we wanted to add a little bit more realism, we can also switch to either of the path traces that are here. So there's the Osprey path tracer, which is also CPU based. And because I have an NVIDIA GPU on my machine, there's also the optics path tracer option, and I'll use that one. Now path tracing is a more advanced way of rendering images. It basically takes all light paths into account, for example, light bouncing off this surface into that direction and then further, etc. So it potentially has can generate much more realistic images, especially when the light starts to creep into places where normally light doesn't reach with raycasting. Because this is optics and using GPU acceleration, the interaction is actually quite good, which is a nice thing. And the main thing to play around with path tracing is this samples per pixels value. This is now set to 2. If I reduce this to 1, you can see that the image becomes a lot more noisy. So what is happening now, there's fewer samples being used to generate this image. And because it's basically an integration problem that's being solved here, it's more noisy. If I increase the samples per pixel to 8, and you can see that the noise level reduces substantially. But it does take more computation to generate this image. So usually you generate a nice path trace image like this from a script or another batch-oriented way. You wouldn't want to do it interactively now because you can see how it influences the interaction speed here. Note that the shadows box has been grayed out now. That's because for path tracing, shadows are basically implicit in the algorithm. The way that the lighting is computed, it's always computing shadows, and there's no way to enable it explicitly. So this also works with things like opacity. For example, we can make this more transparent. But now you will see that the rendering is very slow again. Because what is happening now, the rays that are being traced have to go all through these surfaces. So there's many more computations to be done than when this model is fully opaque. But it can generate very nice images. Right. Yep, there it is. So one thing to notice, as soon as you enable ray tracing here, this is enabled for all objects in the scene. Even though you set it on a particular filter, it actually enables it on all. Which means that one object will shadow another object or another filter output. Okay, so this is for polygonal data, so for surfaces, polygonal mesh. But this data set is actually a volume, as we saw in the exercise. And for volumes, the way to implement or to influence the look and feel and the coloring is very different. It's done using what is called the transfer editor. This is also in the reference page, by the way. So the way volume rendering works is that with each value associated in the 3D grid, basically each voxel of the grid, that value is taken and mapped using the transfer function. So the transfer function is over here. It maps values from the low end of the data range, which is 0, to the high end of the data range, which is 4095. So the low values get mapped to blue, and then the mid-range to white, and the high value range to red, which is what you can see already. But then also the opacity of the voxels are changed. So the low valued values are transparent basically, and that quickly becomes more opaque as you go towards the high values. So the challenge with volume rendering is always setting up the transfer function in such a way that it shows what you want. For example, we can add a point here. Let's say I wanted to highlight the mid-range values a lot more. So by editing the transfer function, I can make sure that only the mid-range values are opaque and the rest is just fully transparent. And now you can see, for example, that we've managed to isolate the skull as the only data that is opaque, and the rest has become transparent. Now, in terms of rendering, this is a bit unrealistic because it's mostly bluish. But again, we can enable shade or shading, as it's called. And now we get a very nice view of this data, much more realistic, while we can still play around with the transfer function to get well, different things out of it. For example, we might want to add part of the skin to give some context to the skull. And now you can see that you've got nicely the skin outlined, but you can see the skull within the skin as well. And this is actually a really nice data set for playing around with this type of volume rendering. But depending on the modality, for example, echo data sets with an echo machine, those are always very noisy and very hard to do good volume rendering on, because setting up the transfer function there isn't easy. In more recent versions of ParaView, there's actually a two-dimensional transfer function editor, which you can update or enable over there. What you do there is you start with a histogram of the scalar value, so that's the value of the data versus the magnitude of the data. And here you can use then two-dimensional areas that are not limited only in value range, but also in gradient magnitude range to select certain parts of the data that need to be visualized. And depending on the type of data that you have in the modality, this can be a better way to do the volume rendering, but it can be tricky to set up correctly. So I just wanted to mention that. Okay, so that was a very brief overview of influencing the appearance, making things look more nice. As I mentioned, within the website, there's more details on this and basically all the steps that I just did. Plugins was a topic that was on the list to explain a little bit about. So as in any software, ParaView has the option to use plugins. There's quite a lot that are built in that come with the ParaView distribution. But there's also plugins that you can find online, for example, for new file formats or different types of rendering or extra filters. You could write them yourself. It does take C++ in the case of ParaView, plus a bit of XML to describe metadata. And the way to use them, so up here under Tools, there's a Manage Plugins window. And these are all the plugins that are distributed with the ParaView binaries. There's quite a lot of them. For example, you might want to activate this plugin from NVIDIA Index by loading it. Now it's loaded. And if we now look up here, oops, let me recreate the view. If we look up here in the representation list, we can see that NVIDIA Index is now there. Now, NVIDIA Index is a volume rendering plugin, which is pretty advanced. So this is now using the NVIDIA volume rendering instead of built-in ParaView rendering. But there's all the other plugins as well. For example, let's take the streamlined representation. Quickly recreate the tornado that you've been using in the exercises. Let's see. Calculator. Okay, so there's our velocity vector as well. And now we switch to the streamlines representation, which might take just a bit. Uh-oh. Yeah, so I think my ParaView is now stuck. Okay, anyways, what that was supposed to show is that with, for example, this Streamlines plugin, you can get animated streamlines within your data. So instead of the static lines, it will actually show particles moving within the tornado flow. You can color them, you can control the length of the streamline and other things. So there's a whole bunch of interesting plugins that you could take a look at some point, just to get a bit more functionality. I have to kill my ParaView because of this. Okay. Then more on parallel rendering and remote visualization of very large data sets. So the main concept of ParaView is this idea of a visualization pipeline. Taking data, applying filters, mapping it to visuals, and then rendering it. Yeah, but then what happens? Suppose that you're working on a HPC system, for example, at Surf, or Stanley is one of your own sites, and you're not using HPC for nothing, you're using it for a reason. Probably because you have a large problem, takes a lot of computation, produces a lot of data. And it would be weird to expect that taking that data and copying it to your laptop, that you can still run visualizations locally because of the scale. For example, local disk storage might become an issue if you have very large data sets. Even if you can store the data locally, they might not fit in your laptop memory or your GPU memory. Or performance of the rendering might be very slow, especially for interactive. So the problem here is that the computation is remote, but the visualization pipeline is running locally. So what ParaView provides is a way to run the whole visualization pipeline in a server, which means that there is a set of server processes, preferably running on the HPC system, that do all the steps, all the filtering, all the mapping, and the rendering, and then only sends over the final image to the ParaView client. And the ParaView client is the exact same GUI application that you've been using so far. So that's a very nice thing. It's basically all transparently happening, all this remote processing, while you can still interact as normally. So here's an example from the University of Amsterdam, a data set, a very large one. This was part of this red blood cell simulation research. This is 2 cubic millimeters of blood in a realistic setting, basically. So it's 8 million blood cells, 500,000 platelets, all packed together very tightly. It's a very large data set, and I wanted to see if there was any funny things going on there, if the algorithm that placed all these cells had produced something that at least looked correctly. So I set up ParaView to run in this client server mode. To the right here, you can see all the server processes. So I used, I think, 28 compute nodes from the supercomputer back then. The data is distributed in chunks. So each of the servers gets one chunk of data. You connect with the ParaView GUI to this running server, and then within the GUI, you can still interact as normally. So all the operations that I'm doing here are just normal mouse handling. While the server processes in the background are making sure that whatever is on my screen is correct. So here you can see the data distribution in the different blocks. You can even color them by the block color. And this is actually quite a large data set. So this is 460 gigabytes of memory in total. It's close to 1 billion cells. So it's a really large scale. But as you can see, the interaction is still quite okay. You might notice that as I interact, the resolution of the image seems to degrade, and that's indeed what is happening. So what ParaView does is, because when you interact, it's more important to have a high update rate, it simply renders the image in a lower resolution within your window. So you can keep interacting smoothly It's only when you stop interacting that it renders it at the full resolution, as you can see. And as you can see, I can just operate on the pipelines normally. I can add a clip filter to clip away half of the data, do other things. And basically the only thing that I had to do was start up these server processes under MPI and then connect to that from the client. Now there are some differences. Because it is a remote connection, you can see up here that we're not connected to built-in, as it used to be called, but now to localhost, because I'm tunneling this through an SSL tunnel from localhost to remote. The memory inspector shows these different server processes. And the most important part is that all the file operations are done on the server side. So you cannot load a file locally from the client that is on your laptop, for example, but it's only remotely. Although I think there have been some changes recently to make that possible. So you can still send over a file that you have locally to these servers. ParaView actually remembers for the different servers that you've connected to what were your recent files, which can be interesting in some certain cases when you use multiple sites that you connect to. And there's a lot of detail in the self-directed tutorial from Kitware. How to set this up, things to optimize, what to think about when using this mode. Like I said, almost in the beginning, it's a bit of a beast to use. And once you get used to it, it's manageable, but there are a lot of aspects that make it somewhat challenging to use this mode. And one of the challenges has to do with the way that the data is distributed. So for example, here we have the head data set split into 4 parts. So we have 4 ParaView server processes, let's say on 4 different nodes. They each render their part of the data, which then gets combined into a single image in the client. Now, conceptually, this is very simple, but one of the issues is how does the data get this distribution? How is that split up? And here file format matters. So for example, on the left side, I've got a .vti file. By the way, this is a different skull here. VTI means VTK image file. So this is a 3D image in this XML file format. I've got ParaView set up here to be connected to 4 server processes on a remote server. And when I load the file in and apply a contour, I can color the different parts of the data by the process ID on which that data is located. So we've got 4 processes, 0 to 3, and the colors correspond to that. And as you can see, the data got distributed automatically. So because this .vta file is a native and modern file format for ParaView, it can read the header of the VTI file on each process and then decide for each process which part to read. And then that makes sure that each of the server processes only reads a part of the data, not all of it, which is exactly what you want. So here the distribution is automatic. But if I use the .vtk, which is the legacy file format, that metadata information isn't enough. So what ParaView does here is it loads the data basically on a single process. It all ends up in process 0. And there's no data distribution, which is exactly what we don't want. So there's a few ways around this. One is to use the D3 filter, which distributes the data after it's been loaded. So we start with the mummy loaded in the VTK file, apply the D3 filter, which then redistributes the data set, and then apply the contour. Now you can see that indeed there's 4 parts to this data again. It's nicely distributed. But it doesn't always work very nice. For example, when we apply it on an ISO service, the D3 filter has issues with making nice subdivisions of the data. So you can see here the brownish color that is located on process 2, I guess, has also some parts that are in a different domain, different spatial domain. So the distribution here isn't very nice. And because of that, the rendering isn't optimized completely either. So this can be an issue. And the other big issue is, of course, you still need to load all the data on one process and then do the distribution, which is exactly not what we want. So the other way to fix this distribution is to make sure that you use the correct file formats. So like I said in the previous example, .vti, that works out of the box, but you can also split manually. For example, you can split in multiple .vti files and then use a single .pvti to gather all those separate files together. So on the bottom here, there's an example. This uses 4 .vti files, each containing part of the full 3D grid, and then a .pvti file to gather those and to refer to those files. When we load this in ParaView, because we already have separate blocks, ParaView makes sure that a block is assigned to a single process and that is not split again, and that the distribution of those blocks over the processes is done fairly. And the same thing more or less holds for the XDMF file format, which I mentioned earlier. So this is an XML file that refers to HDF5 files. So here we have a 3D grid where the spacing is explicitly defined in this grid cohorts.h5 file. And then the associated velocity and pressure values for the node, so that's points in this case, are defined in a separate frame 0001.h5 file. So conceptually, this is very much the same. And depending on the specific type of dataset that you encode in this XDMF file, ParaView will again do this data distribution correctly or not. However, this takes a little bit of experimentation. Usually using a small dataset is to make sure that you don't spend too much time on it. And there's a little bit more information on this wiki page from ParaView, where they go into how does the reading for certain types of data differ in this distribution aspect. Now, a completely different way of doing remote visualization or remote rendering is what we offer at SURF on the Stanley supercomputer. It's using a VNC remote desktop. Probably heard of this. This is really where you have an application desktop running in the cloud, basically, and you connect to that using a VNC client, which is actually a very simple viewer application. So the desktop is remotely running, the application within the desktop is remotely running, in this case ParaView, and all the visualization operations are done within this remote desktop. And then only the remote desktop image, so the windows and the icons, etc., are then streamed to your endpoint, your client. Here's an example where we've got both ParaView running and Blender, in this case, using more or less the same dataset. The way we have this set up at SURF is that even though this is a remote desktop, it still can use GPU accelerated rendering of the GPUs that are in the compute node. So in this case, it's an NVIDIA A100 node that's in there, which is quite powerful. And as you can see, the interaction is pretty smooth. None of the power of your laptop is used. That's all done remotely. This is a very simple way to get even something like ParaView running remotely, close to the data, without having to worry about this client-server mode that I showed before, right? So as long as the compute node that you're using here has more memory and a bigger GPU and more disk space than your laptop, say, that's a win, right? Because then you have access to more resources than you have locally. This is actually a very easy thing. You can use, for example, Turbo VNC as a server, install that yourself on your compute node, run it there, and then connect to it. It doesn't take that much work. And I finally wanted to mention the Jupyter Notebook, not because it is directly related to ParaView, but because it allows you to do scientific visualization as well. There's a few packages for that. So Jupyter Notebook is also a form of splitting up the pipeline and running part of it remotely. Usually it's the data reading and the filtering. And then depending on the exact library that you're using, it might send over the visual elements, for example, the point coordinates, which then get rendered locally in your browser. So not the full pipeline is done remotely. Or it might create an image as well within the browser doing the mapping, and then the rendering is only simply showing an image. And with a library like IPyVolume, which is a Python library, you can then interactively do scientific visualization, for example, extracting an isosurface or showing glyphs within a Jupyter notebook. And for some use cases, that can be an interesting alternative compared to having full-blown ParaView to use. Yeah, I'll skip that. That's not relevant. That's only relevant if you're at Surf. Okay. So then we come to the final topic that I wanted to give you an overview of. Again, there's a reference page with a lot more detail, which is Python scripting. So there's a lot of possibilities with ParaView and scripting. You could write your visualization workflow where you really read the data, apply filters, and write output images for animations and script that, and then run that visualization workflow on many different data sets, for example, in a batch-oriented fashion. So that's one way that you could use Python scripting. Another way is that you can store the current Python state that you have within the application to either the PVSM file or a Python file. I'll show that later. You can even create a custom filter, which might be interesting if you need an operation that isn't in ParaView itself, but you still like to have it as part of your pipeline. I'll show an example later as well. And then finally, there's also a way to create custom plots. You have something that's called a Python view, and then you write a little bit of code, usually using something like matplotlib, with as input data some filter and as output data image, and that can be shown within the ParaView GUI. I've played around with it a little bit. It's a bit buggy and it's not easy to use, so I would not recommend it unless you really want to have a custom plot within ParaView. So looking a little bit closer into scripting, the simplest way to get started is you use something called tracing. So here under Tools, there's an option that's called Start Trace. Usually the defaults are okay, so let's just press OK. And now we can start to interact as normal. Let's say we load the data file from the boy in the CT scan. We add a contour filter like this. And then as a final step, we'll save an image, screenshot, let's say ctscan.png, default options. Okay, and now we stop the trace. And what we now get is the Python script editor. And it contains all the necessary statements for the operations we just did. For example, here's the reader of the VTK file. Then it sets up the render view. Down here is the contour filter being applied. And finally, down here is the screenshot being saved. But as you can see, there's a lot more going on. For example, we interacted with the 3D view at some point. That's being encoded as well. There's also an implicit operation that we did not do ourselves, but that are there actually, for example, setting the coloring to the scalars, updating the view, etc. But we can now save this the script file. Goodbye. And go to our console. Right, so here's the script. And we can execute this script. And there's two ways to do that from the command line. One is there's a pv Python command. And that gives you the regular Python interpreter, but with an added ParaView module there. So if we use pv Python, the execute script, you will see that at some point a window will briefly pop up. And we've now got our CT scan file generated from this script. So this is a really easy way, right? You start this tracing, you do the operation that you'd like, you get a script, and then you can execute it. And then, of course, you can edit the script to, for example, loop over a set of files that you have here, generating a sequence of images for an animation, for example, or different parameters. And this is quite powerful. The other way to run it from the command line is with pv batch. A pv batch is not an interactive application. It's got only a way to run a script. And when I run this, you will see that there's no window popping up here. So the reason for that is that PV Batch has none of the GUI components in it. It's only got what's called off-screen rendering available, so headless rendering, while PV Python has got the full GUI. But another big difference is that PV Batch can be run in this MPI server mode, so you can do parallel processing and parallel rendering of these large data sets, which is something that you cannot do with PV Python. So that was one way to work with the scripting. Another way within the GUI is the Python shell, which adds a window down here. This is again your regular Python prompt as you know it from the command line. And here we can add commands. For example, we can create a wavelet source. It will end up here in the pipeline browser. We can execute commands that are normally done manually within the GUI. So this is a really nice way to interactively experiment with Python scripting to see the effects. You can screw up a little bit in this respect if you use the wrong command. It can get Python or ParaView in a very weird state that's hard to get out of. But it can be a good way. If you want to run a particular script from ParaView, let's say we clear out the scene completely. If we'd like to rerun the script that we just did, we can use the, where's the Python editor? Here. So here's our script still in the editor. And then it should be able to run it. Oh, it doesn't. Let's try. Down here in the Python shell, there is a run script option. We pick a script that we generated earlier. It executes the script, and now we get back what we did. Right, the same operations are being executed, and we get back the scene as it was. So a trace is also a way of saving the state. Another way is to use the save state option here. So we can either use a PVSM file, save that one first, and I'll save to a .py file. And then if we look at these files, the PVSM file is an XML-based file. Again, it's got a lot of details. I suspect it's a better way of saving the state because it's been there, this method has been there for ages in Python, in ParaView. While if we look at Python state, there's fewer statements, I would say. It's still a Python script that you can load in. So it's a very nice way to save state and still be able to edit and replay it. So that's two ways to do the state. There's a very interesting addition in recent versions. It's when you save a screenshot to a PNG file, that's important. We can embed ParaView state in the screenshot. So now over here, we've got this state PNG file. If we look into what's actually within the PNG file metadata, over here, there's a property called ParaView state, which is basically a dump of the XML that we saw earlier. So that's embedded within the image. And it's still an image in every normal sense. Then if we clear the state here and load a new state, it allows you to load a PNG file. Right, so that's a very nice way to combine both what the state shows as a screenshot in the image, but also the state itself. Okay. And then the final thing I wanted to show was how to write a filter in Python. So that's called a programmable filter. There's actually a programmable source as well, which is a filter with no inputs, only outputs. Over here, you can enter a Python script. And within the website, I've got an example for that. So we just copy and paste this piece of code. So what it does is it takes the input data set, particularly the RT data array, takes the minimum and maximum values of that array, and then normalizes the input array to 0, 1 by dividing by the range and subtracting the minimum value and writing that to an output array called normalized. So if we look at the filter output of the programmable filter, there's a normalized array. Its floating point range is 0 to 1, while the original wavelet input range was 37 to 276. So in that way, we've written our custom own operation, our filter, with just a few lines of Python. So this is a really powerful way. And you can do all kinds of crazy things here that you need. And one of the nice things is that ParaView these days contains a NumPy layer to basically wrap the ParaView filter datasets and the filter output in a NumPy compatibility layer, so that we can call things like numpy.min on this data input. You can see it by printing out the type of the dataset. Messages. I need to print the type, not the value. So it is a NumPy interface dataset adapter for a VTK array. So this means that it's not a real VTK array, it just acts like it, but that's good enough for what we need, right? So we can still perform operations like subtracting a value or dividing. So all in all, this is very, very nice way to add, in a light way, more operations to ParaView that you would normally not have. And that's basically what I wanted to show for scripting, and also what I wanted to show in total for the whole course. So stop sharing my screen, and we'll have we have plenty of time for any Q&A or remarks or feedback from your side. Oh yeah, one thing I did want to mention. So within the website, we also have a page called Miscellaneous. There's links to the official user guide, more details on scripting, also Kitware and ParaView have a whole set of tutorials that they produce themselves on all kinds of things. Data analysis, tips and tricks, pictures of movies. So if you'd like to learn more, I would suggest that you look into those. We did add a little interface guide showing the main components. Most of those you should know by now, but if at any point you'd like to reference, it's there. Some information on these different view types. So the 3D render view, the spreadsheet, and some others. And there's some tips of how to get more insight into memory usage, an overall listing of statistics of all the datasets, how to find filter documentation, or how to find a filter, etc. So hopefully that gives you enough to continue learning and working with ParaView. If you have any questions or additions or suggestions, we also like to hear those things, so we can improve the course for others as well. Well, thank you.
Maybe
nice.
I have one question.
Yep.
Well, I have just my personal computer with a graphic card and very powerful servers with a lot of memory and processors, but without a graphic card. So the question is, can I benefit to use ParaView with those servers? Or I need graphic cards on the servers to get some benefits from servers?
Well, the GPU will add some benefit, but it's not strictly necessary. There is a way to use CPU-based software rendering with ParaView, so you should be able to run that on those servers. If you go to the preparations section of the website, under install ParaView, there's a remark on this, that you need to use the min mesa command line option to enable CPU rendering.
Thank you. And the other question, I also see that this ParaView web, is it the same? Just download the web, or it's less powerful?
Well, it depends on what you mean by powerful, because it's basically a web framework to create applications that have this pipeline and then an interactive view.
I mean, functionality is the same functionality or it's not powerful.
Yeah, it is. It is.
Mhm,
Yeah.
thank you.
Question about volume rendering. Computing by summing the data along the line of sight? Yes, more or less. Okay, so you want a maximum intensity projection. I'm not sure that's in ParaView's volume rendering. I'm sure it's in VTK volume rendering, but I actually don't know. There might be an option for the volume rendering settings. I'd need to look into that. I don't know. I haven't seen it. Well, I can add one thing, which is not really related to ParaView directly, but we have 2 Blender courses. And Blender is a 3D animation and a rendering package, and we use that to basically create even nicer animation, even nicer renderings. So next week we have an introduction to scientific visualization with Blender, which is on site in Amsterdam. So please watch for that. And we also have an advanced topic starting next week, which is online. So if you have Blender experience or would like to know more, learn more, you can use the UNCC Netherlands website to see those courses. I'll add the links in the chat. Let's visualize uniform glyphs on unstructured mesh. So you want to take, I guess, the mesh, the points from the unstructured mesh and place glyphs at those positions, or is it a different question?
Hello, can you hear me?
Yep.
Yeah, okay, great. So I don't need to use a chat window. No, I was just wondering, and I have my own approach how to visualize vectors or glyphs on unstructured mesh such that the glyphs appears uniformly as if they were on structured grid. If you know what I mean, it looks better. It looks better in the paper because if I use normal filter glyphs from ParaView, it will of course give me this option to choose seeds and some other parameters, but the vectors will always appear not on like structured grid, if you are getting the point.
Yeah.
So I was wondering if there was some better approach than mine, which is like to make some slices, then cut the slices with another perpendicular slices to achieve to what I want. But I'm not sure if it's possible in some easier way than what I'm using.
Yeah, I think I know what you mean. There is a glyph with custom source, but I'm trying to figure out if that's a custom source for the glyph geometry or for the seed points. Let me check. Yeah, that's for the glyph source. So what you could do is to use, for example, the programmable filter to extract or to define seed points yourself, right, with the associated data values, and then place the glyphs on that. I'm not sure if that's the same to what you're currently doing.
No, it's not. It's not the same. So I use contours twice. So firstly, I made, because in the contours there is this option I can select or I can define a range of values. So I do the slices. It's done basically automatically, and then I apply perpendicular slices to that. And in this way, I can actually also generate a structured field of points, or and then I can show glyphs on these points, but it's somehow not very nice.
Okay.
It's okay.
Okay.
Thank you.
Yeah.
Thank you.
Okay. Well, I guess if we don't have any more questions, Karina, then we can wrap up, or would you have a different proposal?
No, we can certainly, if there are no more questions, we can wrap up. Thank you very much, Paul and Casper, for the course. We can see in the chat that it was very well received and the participants were happy with it. So
yeah, well, thank you all for attending. It's always a fun course for us to do.
Thank you and have a nice rest of the day. Thank you.
Yeah. We'll
Thank
manage.
you.
Thank you.
all.